So we're preparing for really just the last few lectures in the class, which is on integration. Again, Monday morning, 11 o'clock, midterm exam on campus in Gillette Hall. And it covers everything up to, but not including antiderivatives and integration. Antiderivatives and integration do play a very big role in the final exam, so it's very important. And the topic we started to talk about on Monday was area. Area of a region defined by a function. So you might have some function y equals f of x. This is the graph. And we look at the graph from x equal a to x equal b. Let's say the function is non-negative. So we have a certain region in the plane defined by the x-axis, the vertical lines x equal a and x equal b, and the function. And if the function is non-negative, so the graph is above the x-axis, this cuts out this very nice region A, and it has an area which is positive, and it's a positive area. But we take area to be positive or negative if the function were below the x-axis from A to B. Area below the x-axis has a minus sign. So if you have a function like y equals x, and we look at this graph from -1 to +1, it looks like that. So if we want to know the area between the curve, which in this case is just a straight line, and the x-axis, here we have a triangle whose base is 1, whose height is 1. So the area is a half. And this is above the x-axis, so the area is positive. Here, in absolute value, this is a triangle with base 1 and height 1, whose area would also be a half, but below the x-axis, it's negative. So this area is negative and this area is positive. What is the area between this curve and the x-axis? It's 0, because a minus a half plus a half is 0. So it's very important when you're doing calculus to understand that the concept of area comes with a plus or minus sign. Above the x-axis, area is positive. Below, the area is negative. And now suppose we have a function. I'm going to write t as my independent variable now. Y is some function of t. So this is the graph of y as a function of t. Suppose I take a number a and a number x, and I want to look at the curve from a to x. And the region bounded by the vertical lines a and x, the x-axis and the curve, that has a certain area, a, and it's a function of x. If you make x bigger, the area changes. So you fix a, and if you let x vary, you look at the area under the curve from a to x. And what we saw last time is that we can express this as the definite integral, the integral from a to x, f of t dt. So this is a definite integral. This is not the antiderivative of a function. This is the definite integral. The indefinite integral is the antiderivative. Okay. And this is some function of x. As x increases, a of x increases. Of course, if the curve drops below the x-axis, or the t-axis in this case, then the area is positive and this is negative, so the area will start to decrease. So the area can go up and down as a function of x. So we can call this definite integral the area function also. And The hard thing is to calculate these definite integrals or these areas, and that's what the fundamental theorem of calculus tells us. So there are two forms of the fundamental theorem of calculus. I'll write FTC, it's my abbreviation for fundamental theorem of calculus. So it says that if f, a function f, is continuous on the closed interval from a to b, and f is any antiderivative of f on this interval, then, and this is the miraculous fact, the integral from a to b, that is the area under the curve from a to b, f of x dx, is equal to f of b, capital F minus f of a. So if you want to compute a definite integral, you find the antiderivative of the function you are integrating and use this formula. Another notation for this is f of x and vertical line a to b, but this is simply just another notation for this. F of x is called the integrand. A and b are called the limits of integration. So these are just the words that one uses. So for example, suppose we take the parabola y equals 60x minus 6x squared. So this is a quadratic in x squared with a negative coefficient. So this is a parabola opening down. Let's see, what is this? This is 6x times 10 minus x. So this is equal to 0 at x equals 0. It's equal to 0 at 10. And parabola is going to look like that, opening down. So between 0 and 10, this is the graph, and we want to find this area. So the area under the parabola in this region is the integral from 0 to 10 of 60x minus 6x squared dx. Now, the fundamental theorem of calculus says, find the antiderivative, capital F of x, which is the indefinite integral, 60x minus 6x squared dx. The derivative, the integral of x, is a half x squared. So this is 60 times a half x squared. The integral of x squared is x cubed. So what we get for the antiderivative is 30x squared minus 2x cubed. So that's capital F. So this is going to be equal to f at 10 minus f at 0. This is f. So when f is 10, this is 30 times 10 squared minus 2 times 10 cubed. And when x is 0, this is 0. So this is equal to 3,000 minus 2,000, or 1,000. So the area of this parabola, under this parabola from 0 to 10, is 1,000 square units. Okay. I want to spend some time doing many examples of the use of this form of the fundamental theorem of calculus. Suppose I have, this is the definite integral from 4 to 16 of 3 times the square root of x dx. So what does this mean? We have the function y equals the square root 3 times the square root of x. What does that look like? So 0, 4, 8, 12, 16. 4, 8, 12. For this function, when x is 0, it's 0. When x is 4, 3 root 4 is 3 times 2 is 6. When x is 9, 3 root 9 is 9. When x is 16, root 16 is 4. 3 times 4 is 12. So this curve looks like that. And we're asking for the area of this region. So if we want to use the fundamental theorem of calculus, we want to find the antiderivative capital F of x, which is the integral of 3 root x dx, which is 3, I take the 3 outside, square root of x is x to the half dx. A half plus 1 is 3 halves. So this is 3. The integral of x to the 1/2 by the power rule is x to the 3 halves over 3 halves, which is equal to 2x to the 3 halves. So this is equal to f of 16 minus f of 4. F of 16 is 2 times 16 to the 3 halves minus 2 times 4 to the 3 halves. Square root of 16 is 4. 4 cubed is 64 times 2 is 128. Square root of 4 is 2. 2 cubed is 8 times 2 is 16. So we get 112 is the answer. Let's do another example. Suppose we want to find the integral from 0 to 2 pi, this definite integral of 3 sine x dx. So from 0 to 2 pi, this is what the sine looks like. What is the antiderivative of the sine of x? Minus the cosine. So the antiderivative of 3 times the sine of x is minus 3 cosine x. So this integral by the fundamental theorem of calculus is f at 2 pi minus f of 0. That's minus 3 times the cosine of 2 pi minus 3 times the cosine of 0. Cosine of 2 pi is 1, so that's minus 3. Minus times minus is plus. Cosine of 0 is 1. So this is plus 3 is 0. So we have that the area is 0. And if you look at this, you can understand exactly why that has to be the answer. This is the same in absolute value as the area here and here, but this is positive, this is negative. So it's this minus this, they cancel each other out. So the net signed area is 0. That's the story. All right. Any questions? Let's do another example. This one looks more complicated. This is the integral from 1/16 to 1/4 of the function square root of t minus 1 over t dt. Again, it makes no difference what letter we use for the variable, t, x, any letter you like. And notice this is t from 1/16 to 1/4. This is a positive interval, so we're never dividing by 0. But let's simplify this function. Square root of t minus 1 over t is the square root of t over t minus 1 over t. Square root of t over t is 1 over root t minus 1 over t. Or if I write t as 2 powers, this is t to the minus 1/2 minus t to the minus 1. So the antiderivative of root t minus 1 over t dt is the antiderivative of t to the minus 1/2 minus t to the minus 1 dt. What's the antiderivative of t to the minus 1/2? If you add 1 to minus 1/2, you get plus 1/2. So this is t to the 1/2 over 1/2. And the antiderivative of 1 over t is natural log of t. So this is 2 root t minus log t. That's the antiderivative. So this integral is f of 1/4 minus f of 1/16. This is my function f. So that's 2 square root of 1/4 minus the log of 1/4 minus 2 square root of 16 minus the log of 16. Square root of 1/4 is 1/2. That's 2 times 1/2 minus log 4 is the log of 4 to the minus 1 is minus log 4. Minus times minus is plus log 4. Minus 2 square root of 1 over 16 is 1/4 plus the log of 1 over 16, which is minus the log of 16. But 16 is 4 squared, and the log of 4 squared is 2 log 4. So what we get is 1 minus 1/2 log 4 minus 2 log 4 is minus log 4. So that is the answer. So this is an example of the use of what is called the second form of the fundamental theorem of calculus. It's the second form because there's the first form. There's an alternate way to consider the fundamental theorem of calculus, and that's as follows. So think of a function y is some function of t. And you can fix a point A, and that really is fixed, and a variable point x, and we can look at the area between the curve and the x-axis from A to x. So this area which is a function of x, is we write this as the integral from a to x of f of t dt. And as x changes, the area changes. This is a function of x. And it turns out that if f is continuous, if this function is nice and differentiable, it has a derivative. So if this is the second part, this is the alternate form of the fundamental theorem of calculus. If you differentiate this as a function of x, you get back the function, the integrand evaluated of x. That's the that's the fundamental theorem of calculus. Another way to write that is the derivative with respect to x of the integral from a to x f of t dt is equal to f of x. So that's an alternate form of the fundamental theorem of calculus. And so we can say the following. These are some examples. Suppose I take the function sine squared t, and I integrate that from 1 to x. That is, I'm looking at the area under the curve sine squared t from 1 to x. So that's a function of x. And if I differentiate that with respect to the upper limit of integration, I get sine squared x. Suppose I have the function square root of t squared plus 1, and I look at the integral from x to 5 dt. And I want to know what is the derivative of that with respect to x. Now, I have to be careful because the fundamental theorem of calculus applies when the variable is the upper limit of integration and not the lower limit of integration. But one of the properties of the definite integral is if you interchange the upper and lower limits of integration, the sign changes. So this in square brackets is the same as minus the integral from 5 to x, square root of t squared plus 1 dt. Right? If I switch the x and the 5, I have to get a minus sign. And this is now what I'm differentiating with respect to x, which is minus the derivative of this integral, which is the square root of x squared plus 1. Now let's look at a much harder problem. Suppose I have the integral from 0 to x squared of cosine of t squared dt, and I want to differentiate this with respect to x. Again, I have a problem. It doesn't fit directly into the fundamental theorem of calculus format because the upper limit is not x, but x squared. But this is really a composite function. Suppose I define the function g of u to be the integral from 0 to u of cosine of t squared dt. So this is the derivative with respect to x of g of x squared. If I replace u by x squared, this is what I get. And by the chain rule, this is g prime evaluated at x squared times 2x. Now G of U is this. So G prime of U by the fundamental theorem of calculus is the cosine of U squared. So this is equal to, so G prime of X squared is the cosine of X squared squared times 2X, or 2X cosine of X to the fourth. Okay, any questions about this? This is really, first of all, this is new. We haven't talked about this previously. And second, it is very, very, very important. So I want to keep doing exercises using the fundamental theorem of calculus. And I'm simply going to turn to the exercises on page 378. Number 25. The integral from -2 to 3 of x squared minus x minus 6 dx. So I have to find the antiderivative of this function, capital F of x, which is the antiderivative of x squared minus x minus 6 dx. The integral of x squared is a third x cubed. The integral of x is a half x squared. The interval of 6 is 6x. So this is equal to f at 3, capital F at 3, minus f of -2. What is this at 3? This is 27 over 3, 9, minus 9 halves, minus 18. And when I evaluate this at -2, I get -8 over 3, minus 4 over 2, minus 6 times -2 is plus 12. So this looks like, let's see, what is this equal to? 9 minus 18 is -9. Minus 9 halves. So -9 minus 9 halves is minus 27 halves. Minus, what is this? Let's see, this was 12 minus 2 is 10. 10, which is 30 over 3 minus 8 over 3. Is 22 over 3. So if I put this over a common denominator of 6, I get 81 minus 44. So if my arithmetic is correct, I get minus 37 over 6. But you need to check the arithmetic. The problem asks us to actually sketch the graph of the function and shade the area we just found. So let's see, x squared minus x minus 6. This actually factors into x minus 3, x plus 2. So this is a parabola which opens up. It's 0 at 3. It's 0 at -2. It's minus 6 at 0. And so this parabola is going to look something like this. And from -2 to 3 is completely below the x-axis. So that's the region that we're graphing, and this area is minus 37/6. Look at number 26. We have the function x minus the square root of x, and we want to find the area under the curve from 0 to 1. So the antiderivative, capital F of x, is the integral of x minus square root of x, or the integral of x minus x to the 1/2. The integral of x is a half x squared. The integral of x to the 1/2, if you add 1 to a half, you get 3/2. So it's minus 2/3 x to the 3/2. So this is equal to f of 1 minus f of 0 for this capital F. When x is 1, you get a half minus 2/3. And when x is 0, you get 0. And a half minus 2/3 is minus a 1/6. Oops. So this looks like it's negative. So let's graph this function. It's kind of interesting. So x minus the square root of x from 0 to 1. So if I have f of x equals x minus the square root of x, that's 0 at 0. It's 0 at 1. And in between, x minus the square root of x is less than 0. So x is less than the square root of x, or square root of x is less than 1, greater than 0. So this function is negative from 0 to 1. So we expect the area to be negative, because area below the x-axis is negative. And that's exactly what we got. All right, so this is really useful practice. Let's do a couple more. Suppose we have, let's look at number 50. The integral 1/2, the integral of from 0 to the log of 2 of e to the x dx. Now, the indefinite integral or antiderivative of e to the x is just e to the x. So this is 1/2. And what is this integral? F of log 2 minus f of 0. That's 1/2 e to the log 2 minus e to the 0. E to the log 2 is 2, e to the 0 is 1, 2 minus 1 is 1, so the answer is a half. Suppose we have the following function. This is number 61. Suppose f of x is defined as follows. It's equal to sine x plus 1 if x is less than or equal to 2, and it's equal to 2x plus 5 if it's equal to sine x plus 1 if x is less than or equal to pi over 2. Legibly, if x is less than or equal to pi over 2, and it's equal to 2 cosine x plus 2 if x is greater than pi over 2. Let's see. What does the graph of this function look like? So sine of pi over 2 is 1. So sine of pi over 2 plus 1 is 2. And for x less than or equal to pi over 2, this is just the sine function. Sine of minus pi over 2 is minus 1 plus 1 is 0. So this function is just oscillating like the sine, less than or equal to pi over 2. When x is equal to pi over 2, the cosine of pi over 2 is 0, and 0 plus 2 is 2. So this function, let's see, when x is pi, cosine of pi is minus 1. You get minus 2 plus 2 is 0. And this function is going to oscillate like this. This goes from 0 to 4. So that's the graph of this function. And we want to compute the integral from 0 to pi of f of x dx. So that's the area of this. So it's this rather complicated region. And we can use the fact that this area is the sum of two areas. It's this plus this. So this is the integral from 0 to pi over 2 f of x dx, plus the area from pi over 2 to pi. Now from 0 to pi over 2, this function is sine x plus 1. So this is the integral from 0 to pi over 2 sine x plus 1 dx. And from pi over 2 to pi, this function is 2 cosine x plus 2. So to solve this problem, to calculate this area, we have to compute two different integrals. What are the antiderivatives? The antiderivative of sine x plus 1 dx, the antiderivative of the sine is minus cosine x, and the antiderivative of 1 is x. I can write this as x minus cosine x. And suppose I let capital G of x be the antiderivative of 2 cosine x plus 2 dx. The antiderivative of the cosine is the sine, and the antiderivative of 2 is 2x. So this is equal to this integral, which is capital F of pi over 2 minus capital F of 0, plus this integral, which is capital G of pi minus capital G pi over 2. What is f of pi over 2? When x is pi over 2, you get pi over 2 minus 0. And when x is 0, you get 0 minus cosine of 0, which is -1. What is g of pi? Sine pi is 0, so this is 2 pi minus g of pi over 2. When x is pi over 2, sine pi over 2 is 1. This is 2 plus 2 times 2 pi, which is pi. So this is minus 2 plus 2 pi. So what I have is pi over 2 plus 1 2 pi minus 2 pi minus 2. So if I did my algebra correctly, pi over 2 minus 1 is the answer. All right, any questions about these? These are definite integrals. This calculates some derivatives of integrals. So this is number 73 on page 379. The derivative with respect to x of the integral from 3 to x, t squared plus t plus 1 dt. Directly from the fundamental theorem of calculus, the derivative of this integral where the variable is the upper limit of integration, you just take the integrand and you let t equal x. And that's the whole answer. If we have the integral from x to 1 of the square root of t to the 4th plus 1 dt, and we want to differentiate that with respect to x, you can't use the fundamental theorem of calculus directly because the variable of integration the variable that you're differentiating has to be the upper and not the lower limit of integration. But if you interchange upper and lower limits of integration, you change the sign. This is minus the integral from 1 to x, square root of t to the 4th plus 1 dt. So that's minus the derivative of this, which is square root of x to the 4th plus 1. This was number 75. Let me go back and look at this for a second. So here I use the fundamental theorem of calculus, but I could also do it directly, because if we have the integral from 3 to x of t squared plus t plus 1 dt, I can actually compute this integral. The antiderivative, let's say f of t squared plus t plus 1 dt is what? The integral of t squared is a third t cubed. The integral of t is a half t squared, and the integral of 1 is t. So this is equal to f of x minus f of 3. That's a third x cubed plus a half x squared plus x minus f of 3. F of 3 is a third 3 cubed plus a half 3 squared plus 3. This is 27 over 3 is 9 plus 9 halves plus 3 So that's 12, that's 16 and a half. 33 over 2. So that's this function of x. And if I differentiate this, when I differentiate this, I get x squared plus x plus 1. And that's exactly what I got above using the fundamental theorem of calculus. So there's some nice consistency in all of this. Let's look at something a little more complicated where we have a kind of a chain rule. Suppose I have the integral from 2 to x cubed of 1 over p cubed dp. And I have this function, and I want to differentiate with respect to x. Now, here the difficulty is that the upper limit of integration is not x, it's x cubed. So suppose I define a function f of x to be the integral f of u to be the integral from 2 to u dp over p cubed. Then f of x cubed is the integral from 2 to x cubed dp over p cubed. So what I'm differentiating here is f of x cubed. And by the chain rule, that's f prime of x cubed times 3x squared. Now this is f of u. What is f prime of u? That's 1 over u cubed by the fundamental theorem of calculus. So f prime of x cubed is equal to 1 over x cubed times 3x squared. So this is 3x squared over x to the 9th, or 3 over x to the 7th. That's number 77. Let me just double check, because it's always easy to make mistakes. Oh, yeah, so actually, what I did is correct, but I copied the problem down wrong. So this problem was differentiate with respect to x, the integral from 2 to x cubed of 1 over p squared. So f of u is the integral from 2 to u of p squared. So the derivative f prime of u is 1 over u squared. So this is f prime of f of x cubed, that's f prime of x cubed 3x squared. When I evaluate this at u x cubed, I get x cubed squared 3x squared. This is x to the 6th, so this is 3 over x to the 4th. So what I did was correct, but I solved a different problem. Let's look at another example. Suppose I have the integral from minus x to x of the square root of 1 plus t squared dt. And I want to differentiate that with respect to x. So this is a little more complicated, and we have to analyze this somewhat carefully. Let me write this down again. I have the integral from minus x to x of the square root of 1 plus t squared dt. So I can write this as the sum of two integrals. This is the integral from minus x to 0, square root of 1 plus t squared dt, plus the integral from 0 to x, square root of 1 plus t squared dt. Let's just draw a picture. What is the function y equal the square root of 1 plus t squared look like? So it's always above the x-axis. And when t is 0, it's 1. And this is increasing like that. And it's symmetric, so it's might look something like this. So we want the integral from minus x to x. So that's the integral from minus x to 0 plus the integral from 0 to x. And then we reverse the limits of integration. So this is minus the integral from 0 to minus x, square root of 1 plus t squared dt, plus the integral from 0 to x, square root of 1 plus t squared dt. And I want to differentiate this with respect to x. So suppose I let f of u be the integral from 0 to u of the square root of 1 plus t squared dt. So this integral from minus x to x, square root of 1 plus t squared dt, is minus f of minus x plus f of x. So if I differentiate with respect to x, I get minus f prime at minus x times the derivative of minus x, which is minus 1, plus f prime of x. F prime of u is the square root of 1 plus u squared. So this is minus times minus is plus. This is f prime of minus x, that's the square root of 1 plus x squared, plus another square root of 1 plus x squared. So I get 2 times the square root of 1 plus x squared. That's the answer. So I really encourage you to spend a lot of time learning these methods of applying the fundamental theorem of calculus. I can make some other remarks about integrals. So let's say a function f of x is even if f of minus x equals f of x for all x. So this is a function which is symmetric with respect to the y-axis. When you graph this function, whatever it is on the plus side is the same on the minus side. If you were to rotate this around the y-axis, you would get the same thing. And if you're integrating over a symmetric interval, say from minus a to plus a, this area is going to equal this area. So for a symmetric function, the integral from minus a to plus a, f of x dx, is exactly twice the integral from 0 to a of f of x dx. That is, this area on the left equals the area on the right, so the total area is just 2 times the area on the right. We say f is an odd function if f of minus x equals minus f of x. So this is a function which is somehow symmetric through the origin. Like f of x equal x cubed, here is positive, and here is exactly the opposite, it's negative. And again, if you look at a symmetric interval from minus a to a, this area is going to be equal in absolute value, but opposite in sign to this area. And then we'll cancel. So for an odd function, an integral over an interval from minus a to plus a is always 0. And there's one other notion that's very useful, which is the average value of a function. So the average value of a function f of x on the interval from a to b is defined to be the f bar for average. It's the integral from a to b divided by the length of the interval, 1 over b minus a. And there's a certain mean value theorem for integrals, which says that the average value of the function, 1 over b minus a, the integral from a to b, f of x dx, is actually the value of the function, f of c, for some c between a and b in the open interval from a to b. Okay, well, we'll look at this more after the midterm, but I think we've covered a lot today, and I don't want to go any further. Are there any questions about anything we've done on integration or any of the topics that'll be on the midterm? Optimization, all the rules for differentiation and so forth? All right, well, if not, then we will end for the morning. And if you look at the announcements on Blackboard, you'll see I have posted office hours today, tomorrow, Friday, and I'll also add something on Sunday if you have any last minute questions. And then I'll see you all in person Monday morning. Okay. Bye all.